Okay, we're recording, so be quiet. Or I'll tell your parents. All right, so anyway, this is the graph of y equals tangent of x. And the reason that this looks like it does is because you get the values of y equals tangent of x off the unit circle. For instance, this would be, Jason, the tangent of pi over 4. Can anyone tell me without looking? Because you're going to need to know this for your test. What is the tangent of pi over 4? 1. Okay? So this point is, because it's rooted 2 over 2, right? If I had the unit circle over here, okay? It's over root of 2 over 2 and up root of 2 over 2, right? And so root of 2 over 2 over root of 2 over 2 is 1. And that's why we get this, okay? The next, if I want to graph another point, like say the tangent of pi over 3 or 6 degrees, it's going to be, well, it's going to be root of 3 over 2 over 1/2, right? Which gives you root of 3, which is about 1.73. So this would be the point on there, for instance, the pi over 3, comma, root of 3, which is about 1.7 something, okay? And you can see that as tangent gets closer and closer and closer to 90 degrees, I say I'm really, really close here. This number gets really, really small, right? And this number gets really, really big. And that's why you have an asymptote here, because the y over the x goes to infinity. And that's why I have an asymptote down here, because if I go this direction, then the y is negative, right? And the x is positive, and you get a really big negative number. So that's what y equals tangent of x looks like. And as you can see, it repeats itself every pi radian, not every 2 pi radian. So when you're looking for the period, you know that formula I gave you for sine function? Period equals 2 pi over the frequency, or they call this b or omega over here. For a tangent function and a cotangent function, that formula changes to period equals pi over the frequency, okay? So this is for sine and cosine, but this one and cosecant and secant. So use this formula when you're dealing with pi. And likewise, b is equal to pi over the period, or tangent. So the domain of this is just x is not equal to, can I go down? X is not equal to pi over 2 plus pi, I think they use the letter k, where k is an integer, okay? So in other words, you cannot have any values that are pi over 2 plus or minus any even multiple of pi, okay? So pi over 2 plus pi gets you to 3 pi over 2, right? Minus pi gets you to minus pi over 2. Minus 2 pi gets you to minus 3 pi over 2. So that's what that means. It's pi over 2 plus a multiple of pi. This function is undefined, which is the same thing almost, where the only thing that changes for this and the vertical asymptotes is that's an equal sign instead of a not equal to sign. Pi over 2 plus pi k, where k is an integer. Okay? And then the range of this goes from negative infinity up to infinity. So tangent can go from negative infinity to infinity. So it's negative infinity up to infinity, or all real, whatever you want to call it. All real? All real numbers. Okay? And the period, like I said up here, is pi. And the x-intercepts for a tangent are here at 0 and at pi. right? It's 0, pi, 2 pi, negative pi. So those are just all the multiples of pi. And that's all the place where tangent equals 0, which is here, here. If I were looking at a unit circle, here, 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 as many times as I want to go around. So x equals, we'll just call it pi k, where k is a whole number, right? Negative pi, okay? Okay? So graph y equals tan 2 tan x. All that does to your graph, I didn't put a graph in there, did I? Do you guys have one on your sheet? Oh, it's the next one. So if I were to graph 2 tan x, all that does is it stretches this thing out. So I'm just going to kind of sketch it. Okay, so if I were going to graph 2 tan x, all it does is it multiplies all those y values by 2. And so what it would look like, instead of this being the point pi over 4, 1, it would be the point pi over 4, 2. And instead of this being the point pi over 3, 1.7, it would be pi over 3, 3.4. Right? So basically what it does is in here it actually makes it kind of squishier. But then as you go out, it makes it steeper. So it kind of goes like this. And then it kind of goes through like this. And then it pulls, it's like you're pulling on the end of things, right? So it just stretches it vertically. Okay? Great. Okay. So that's y equals tangent x. So now if I want to graph this more complicated one, okay, I kind of cheated. I got some better graph paper than you have, okay? And I should have put that on there, but I didn't have time because it was late last night when I was looking at this and I was tired. So what negative tangent does, that flips the direction, makes it go like this instead of going like this. And what this does, it shifts it which way? Which way does that shift it? Left, pi over 4 radians. So instead of me having asymptotes here and here, okay, one period of it, the asymptote would be shifted, the asymptotes would be shifted to negative 3 pi over 4. That's not very slow. Come on, you can do it. Okay. Would be shifted here. Let me try. That's still not so good. That's not good. Okay. The asymptotes would be there and then move back pi over 4 to there. Okay. And then if you might want to pick some points, okay, but it's not stretched vertically or anything like that. But where I had 0, 0, now I have that. Then I have negative pi over 4, 0. And where I had negative 1, now I have a positive 1. And then kind of like where I had a positive 1, now I have a negative 1. So this graph kind of looks something like, that's pretty good. No, that's not very good. It's not. You get it. So basically it shifted left pi over 4 radians and it's flipped direction. Okay? And then you could sketch, that's just one period of it, so then you'd want to keep going a couple times to show that you know it repeats itself every pi radian, something like that. Okay? I'm getting worse. But that's what it would look like. Okay? What? Almost the same as a cotangent. Cotangent has, so that's the next thing. Cotangent, which is the next one, it looks like this. So cotangent comes from the top left, but it's shifted over pi over 2, not just pi over 4, right? So it's actually shifted, what the heck? Stop doing those things. Stop, okay? So So yeah, if I took tangent and moved it, stop. If I took tangent and moved it, I guess left pi over 2 and made it negative, then it'll look like that. So for cotangent, the domain is x is not equal to pi k, so not equal to even multiples of pi, so it can't be, this is 0, right? So 0, k is an integer. What's that little thingy? Go away. I don't know what that is, but it's there. Okay, so it's not equal to multiples of pi. The range is all real. All real. The period again is still pi. The vertical asymptotes are the same as the domain with an equal sign. X equals pi k. And the x-intercepts are here, here, here. So it kind of flips from what tangent had. So the x-intercepts are pi over 2 plus pi k, where k is an integer. Okay? And that's that. So this is what the graph of cotangent looks like. Starts at on the y-axis and it comes down and it goes until it hits pi, and then it keeps repeating like that. And so then if I want to graph y equals 1/2 cotangent of x, the only thing, what's that going to do? Spread it out, or is that going to make it go faster or slower? Slower. Yeah, like Logan said, it's going to make it stretch out, because for this one, the period is going to be equal to pi divided by 1/2, which is 2 pi. So if I want to graph y equals cotangent of 1/2 x, so it takes 2 pi to complete one cycle, so I would have like an asymptote here, okay? And then it would just come down this way and go half as fast. So at pi you would be at 1, is that? Yeah, I think at pi you would be at 1. And so you come down like this and do that, and it would take, alright? Wait a minute. 0 to 2 pi. Oh no, I have 0 there, that's right. Okay. So you'd have a, you go through 0 there, sorry. So it come down like this, and go through 1 there, and then through negative 1 there, like that. Are we good with that? And it repeats itself forever and ever and ever. Okay. And then we have the graphs of secant and cosecant. Did I tell you this? I told you that joke, right?
Yeah.
What? What? Do you think that John can tell us what 1 over cosine is, or 1 over sine is? Cosecant. Cosecant.
Was not.
So what's 1 over sine? Cosecant. Okay, let's continue. So this is the graph of secant, and if you remember that secant is equal to, so secant x is equal to 1 over the cosine of x, right? So where the secant graph comes from is by graphing the cosine values, and then you take the reciprocal of all those values. So this is the graph of cosine. So this is kind of a weird graph, and then this says 6 here. This is actually like 2 pi, right? This was the best I could do, but now I'm better at finding graphs. And so this would be pi right here, and this would be 0. So the way that you graph secant is by graphing cosine. And since the cosine of 0 is 1, the reciprocal of 1 is 1, right? And then since the cosine of, this would be pi over 2, since the cosine of pi over 2 is 0, what you have everywhere there's a multiple of pi over 2 is an asymptote, because the reciprocal of 0 is undefined. So you have asymptotes every place that there is a 0 with cosine. Okay, so these are asymptotes right here. So if you draw a graph, if I ask you to sketch, that's really bad. But if I ask you to graph the secant or cosecant function, and you show these little things crossing these vertical lines, that's bad, because it's showing you don't know that it's an asymptote. Okay, so you have asymptotes every multiple of pi over 2. So the domain for this one is x is not equal to pi over 2 plus pi k. Again, the range goes from y is greater than or equal to what? Hello? 1, and less than or equal to negative 1. So secant and cosecant are undefined. I mean, they don't have any values. You always get a value bigger than 1 or less than negative. Because it's a reciprocal. Because sine and cosine, they only go between negative 1 and 1, right? So the reciprocal of a number between negative 1 and 1 is going to be a number bigger than negative 1 or 1, okay? And the vertical asymptotes are the same as this with an equal sign. So x equals pi over 2 plus pi k. And then the x-intercepts they don't have any, right? Are there any x-intercepts that you see? Hello? No. None. There is a y-intercept, one of them. Y-intercept of 0, 1. Right? And the period is 2 pi. You can see, right? It repeats itself every 2 pi. So here's 1, and then it continues again. The same thing starts again at 2 pi. Okay? So it's periodic the same way sine and cosine are. Okay? Getting to the next thing, I know it's a lot, but gotta go. Okay? This is y equals cosecant x, and this is right here. This is y equals sine of x, right? And to graph cosecant, you take, that's why you take 1 over sine of x. And so since this would be pi over 2 right here, the sine of pi over 2 is 1, and so the reciprocal of 1 is 1, and that's why you have a point right there. And then the sine of 0 is 0, and the reciprocal of 0 is undefined, that's why you have an asymptote right there. And there's asymptotes here, 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 and here. So the domain is x is not equal to pi 2 pi k. Did I say 2 pi k in the last one? Or did I say? Oh no, that's right. X, that was right. X is not equal to pi k because you have asymptotes every pi radius. Okay. The range is same as for secant. Y is greater than or equal to 1, or y is less than or equal to negative 1. The period is 2 pi. The vertical asymptotes are the same as this. X equals pi k. And the x-intercepts, there are none. Okay, and there's no y-intercept here. Alright? So, how do I graph something like this? I'll show you. How much time we got? The way you graph something like this is by first graphing y equals 2 sine pi x plus 1. Okay? So for this, we know the amplitude is 2. We know the period is going to be 2 pi divided by 2, which is, 2 pi divided by pi, right? Which is 2. Okay? So this thing is going to complete one cycle every 2 radians. So if this is 1 radian, this is 2 radians. So when you see graphs that just have numbers like this, there's -1, okay? And so on and so forth. And it's going to be shifted up 1, right? So let me just try to sketch that in a different color up here to make it even less more dotted than this. So if I start here and go to here, this is your vertical shift line, right? And so this sine function there's no horizontal shift, so it's going to start here, it's going to go up to, this is the line y equals 1, okay? It's going to go up to from here, and it's going to complete one cycle in 2 radians. So it's going to go up 2 from here, okay? And then it's going to go down 2 from here, which will put you down here at -1. So this would look, the sine function would look something vaguely like this, okay? And up here, hi John. That's really bad. John messed me up, okay? So I come down here, thanks. Is that for freshman seminar?
Yep.
Okay. So I go down here through here and like that, and then it would continue like that forever, okay? And then what you do is you sketch in the asymptotes everywhere this thing would have, would cross that midline. Okay, so there's an asymptote here, there should be an asymptote here, and then you sketch in your cosecant function. The minimum of the cosecant function is where the maximum of the sine function should be, and the maximum of the cosecant function is where the minimum of the sine function would be. And I'm not worried about specific values, just so long as you can show me that you understand where the asymptotes are in the period and the zeros and stuff like that. Okay, do you understand that? So first you sketch the sine wave, and then you put in the asymptotes everywhere this thing would be crossing that axis, and then you just sketch in the cosecant. So the cosecant is not, I should make this part dotted, but that's about it. Okay? You get that?